Deep within the steel belly of a cargo vessel, the engine room is normally a deafening environment of extreme heat and vibration. But here, in drydock, after 16,000 hours of continuous global trading, the propulsion plant sits completely cold and motionless. The engine does not stop and cool on command. The sheer thermal mass of thousands of tons of cast iron, forged steel, and circulating jacket water means it takes well over 48 hours for the metal to cool sufficiently for engineers to safely enter the crankcase. This forced immobilization provides the only opportunity for a comprehensive machinery overhaul. Heavy shipyard cranes, shore-based specialists, and classification society surveyors execute invasive dismantling procedures that are physically and legally impossible while the vessel is pitching and rolling at sea. The work performed here relies on a distinct mechanical paradox. Engineers must disassemble components of colossal physical scale and weight, specifically to locate and correct internal wear that is measured in microscopic increments. The ultimate objective of this process is absolute thermodynamic efficiency. By forensically measuring, diagnosing, and rebuilding the plant, the engineering team works to restore the engine's baseline specific fuel oil consumption. This is a rigid, data-driven intervention. The survival of multi-ton steel components is dictated entirely by uncompromising mathematical thresholds set by classification societies. The manufacturer-mandated maintenance schedule flags 16,000 running hours as the exact trigger point for the single most intensive operation in the engine room, the main engine piston drawout. The reciprocating assembly of a modern two-stroke marine engine operates on a staggering scale. A single piston has a stroke length of 2 meters, a bore diameter approaching 1 meter, and an assembled mass of over 800 kilograms. Once the piston is hoisted clear of the cylinder, engineers immediately examine the crown. They search for deep thermal fatigue cracking and localized hard carbon deposits, physical markers indicating poor fuel atomization or irregularities in the combustion chamber. Further down the assembly, the piston rings are checked for absolute groove freedom. Each individual ring must expand radially outward without sticking. Any restriction destroys the ring's ability to seal combustion pressures against the cylinder wall. With the piston removed, surveyors descend into the empty cast iron block to gauge the internal bore of the cylinder liner. They take internal diameter measurements at multiple heights, looking for peak wear at top dead center, the exact point where thermal load peaks and the lubricating oil film is at its thinnest. In this cylinder liner cross-section, we see exactly where metal deteriorates. Localized material loss at top dead center creates a distinct wear pattern. The manufacturer's absolute wear limit is 0.8 millimeters, but here the measured wear extends to 1.1 millimeters. Because that measurement exceeds the safety threshold by 0.3 of a millimeter, the entire multi-ton cast iron cylinder liner is officially condemned and must be completely replaced. While the cylinder blocks remain open, the heavy steel cylinder covers undergo their own high-pressure overhaul. The high-pressure fuel injectors are extracted and transported to a dedicated test bench. The test bench validates 2 exact parameters. First, the injector's opening pressure must crack perfectly between 300 and 350 bar. Second, the nozzle must produce a perfectly symmetrical atomization spray pattern, completely free from any dripping or streaking. Surrounding the injectors are the starting air valves. Failing to completely overhaul these valves carries severe safety consequences. A leaking valve allows unburned oil vapor to backflow, creating the conditions for a violent detonation directly inside the air manifold. The combustion air itself is supplied by the engine's forced induction system. The engine relies entirely on the turbocharger, a machine responsible for more than doubling total power output. During a turbocharger overhaul, the single most critical diagnostic measurement is the K value. This specific metric defines the axial clearance of the entire thrust-bearing assembly. This schematic of the rotor shaft shows the K value. It is the microscopic axial gap measured between the turbine nozzle ring and the turbine blades. This clearance is vital because of the extreme operating environment. In service, this multi-ton rotor assembly spins at extreme rotational speeds, reaching up to 25,000 revolutions per minute. At those extreme speeds, any physical imperfection generates devastating rotational forces. To survive, the entire rotor requires dynamic balancing on a specialized machine. correcting unbalance down to the individual milligram. If the rotor assembly fails to meet the required K value or balancing tolerances, vibration will destroy its own high-speed bearings within hours, instantly crippling the ship's propulsion system. Away from the towering main engine sits a bank of 4-stroke medium-speed diesel generator sets. These units provide the electrical lifeblood for the entire vessel. These auxiliary generators operate at much higher rotational speeds, typically 720 to 900 RPM. They endure rapid transient electrical loads as heavy consumers cut in and out, causing accelerated component cycling and intense thermal stress. To diagnose the structural health of these hard-working engines, marine engineers use crankshaft deflection. It functions as a highly precise stethoscope for the engine's mechanical heart. Technicians wedge a sensitive dial gauge between two adjacent crankwebs. Using the turning gear, they rotate the massive steel crankshaft through 4 cardinal positions, tracking how much the heavy steel webs flex under their own weight. This diagram demonstrates how the crankweb flexes. The overlay dial gauge shows a maximum acceptable deflection threshold of plus or minus 0.10 millimeters. If the needle sweeps past that safe zone to 0.12, it explicitly proves severe adjacent bearing wear. Ignoring excessive deflection creates a predictable path of destruction. As the bearing wear increases, the crankshaft bends further with every rotation, leading directly to fatigue cracking and eventual total shaft failure at sea. Above the crankshaft, the generator's governor mechanism modulates the fuel supply. It must react instantly to transient load swings to maintain a perfectly stable electrical frequency across the ship's grid. Managing these microscopic structural tolerances and rotational speeds is the only way to guarantee that the ship's navigation, cooling, and cargo systems retain uninterrupted power. The combustion blocks require an intricate network of circulatory and thermal management systems to keep the machinery alive. The centrifugal purifiers sit at the start of the fuel cycle. These high-speed rotating machines spin heavy fuel oil, utilizing extreme G-forces to forcibly separate out water and highly abrasive solid impurities before they can reach the engine. Inside the spinning bowl, the correct sizing of the gravity disc dictates the critical boundary interface. It holds the line between the cleaned oil and the separated water. Downstream, massive seawater heat exchangers manage the extreme temperatures. In service, they face a constant accumulation of microscopic marine biofouling and hard mineral scale coating the internal tube bundles. A single central cooler handles 600 tons of seawater per hour at full load. Fouling inside those tubes causes a 40%. As the inspection concludes, delicate measuring gauges are replaced by high-pressure hydraulic tools. The multi-ton cylinder covers are lowered back into place and torqued down. With the turning gear disengaged and starting air applied, the heavy internal components finally cycle back into motion. The specific fuel oil consumption baseline is recovered. Thermal margins are restored. The structural integrity of the rotating assembly is secured for another 16,000 hours of continuous operation. The internal mechanical heart of the vessel is now perfected. But outside the hull, resting on the drydock blocks, the ship's external hydrodynamic efficiency and steel corrosion present the next engineering challenge.